Welcome back to The Explainer. Today, we're taking a pretty fascinating journey into the microscopic world. We're going to track exactly what happens to a substance as it loses heat, transforming all the way from a wildly energetic gas down to a rigid, frozen solid.
Okay, let's dive into this, because there is actually a massive mystery hidden in plain sight when things get cold. Imagine you take a hot gas and you continuously cool it down, like you are literally extracting heat from it nonstop in a controlled environment. You'd expect the temperature to just keep dropping and dropping, right? But it doesn't. Sometimes the temperature completely flatlines. It just stops dropping, even though you are still constantly cooling it. Why on earth does it do that? To solve this, we're going to map out the hidden physics of cooling states. We'll start with the cooling curve mystery, then look at region A as the gas cools, investigate the condensation and freezing plateaus, and finally, we'll contrast exothermic and endothermic reactions. Part 1. The cooling curve mystery. What's really interesting about this slide is how we actually map the shape of a cooling curve over time. Picture a thermometer in a hot swirling gas. As time ticks by, we pull heat away. Now look at the timeline here. At T0, the gas cools, and the temperature drops sharply, exactly like you'd expect. But at T equals -2 minutes, it flatlines. This is the condensation plateau. It drops again as a liquid at T equals -4, but at T equals -6, freezing begins, and boom, another flatline. It holds steady again before finally dropping as a solid at T equals 8. Our whole job today is to interpret exactly what causes those bizarre stalls. Moving into Section 2, Region A, the gas cools. So right at the start of our curve, we've got a gas. The particles are just bouncing around chaotically, full of kinetic energy. But as we continuously remove heat from the environment, this incredibly logical sequence of events kicks off. Step 1, the internal energy of the particles decreases. And because they have less energy, Step 2 happens. They move much more slowly. They aren't smashing into each other with that same violent force anymore. And because they're slowing down, we reach Step 3, the particles actually begin to drift closer and come together. This slowing down is exactly what causes that initial steep drop in temperature on our graph, totally setting the stage for the first big phase change. Which brings us to Section 3, the condensation plateau. Okay, we've hit our first major mystery point. The substance is turning into a liquid, but the thermometer has completely stalled out. Why? Well, the crucial thing to understand here is intermolecular forces. Basically, these are the weak attractive forces that act between molecules. Think of them like microscopic magnets. For substances like water or ethanol, as the molecules slow down and get close enough together, these exact forces reach out and start pulling the molecules into a much more organized structure. Let's break down the actual mechanics of what happens when those microscopic magnets click together. As the particles come closer together during condensation, those new intermolecular forces of interaction take place. But here is the secret to the whole shebang. Creating these bonds isn't a passive process at all. When these forces form and lock the particles into a liquid state, energy is actually given out to the surroundings. The very act of bonding literally releases heat. And that right there solves our first mystery. The energy being released perfectly counteracts the external cooling, which keeps the temperature entirely unchanged until the liquid is totally formed. So even though we are actively trying to cool the substance down from the outside, the substance is generating its own internal heat as those particles snap together. It's this epic microscopic tug-of-war, and it completely stalls the macroscopic thermometer until every last particle has condensed. All right, Section 4, the freezing plateau. Moving further down the timeline to Region B, our liquid cools and the particles lose even more kinetic energy. They basically slow down to a crawl until a solid begins to form. And this brilliantly illustrates a repeating pattern. At this threshold, those rigid forces holding the solid together form and lock into place. We see the exact same tug-of-war repeat itself. The freezing process releases energy once again, giving us that second stubborn flat line on our cooling curve until the entire puddle is frozen solid. Now, once every last drop of liquid has transformed into solid ice, there just aren't any more bonds left to form. The energy release just stops. So after freezing is complete, we enter Region C. The temperature finally drops again, and the solid just gets colder, with its tightly packed particles merely vibrating less and less strongly as the temperature plummets. Section 5. Exothermic versus endothermic. Let's step back for a second to look at the bigger picture of energy transfer. We generally classify these phase changes into two camps. On the left, we have exothermic changes. Exo meaning outside, thermic meaning heat, so these release heat into their surroundings. On the right, we have endothermic changes. Endo meaning inside, meaning these absorb heat from their surroundings. Let's walk through this table together to really lock this concept in. Look at the exothermic row first. The phase changes we just tracked on our cooling curve, condensation and freezing, are exothermic. Heat is released to the surroundings as particles bond together, and mathematically we represent that with a negative delta H value. But what if we reverse the whole experiment? If we start with a solid and add heat, we get a heating curve. This involves endothermic phase changes, like melting, evaporation, and boiling. Here, heat is taken in from the surroundings. Why? Well, because you have to physically inject energy into the system to rip those particle interactions apart. That added energy breaks the bonds, which is exactly why endothermic changes have a positive delta H value.
You know, I absolutely love this quote from our source material because it sums up everything we've uncovered today. The way the particles in the three states are arranged and interact with each other also helps to explain the energy changes. It's such a great reminder that to truly understand the macro world, like a flatlining thermometer or a freezing lake, you always have to zoom into the micro world of particle interactions.
So I want to leave you with a question to ponder. Knowing that phase changes involve these massive, hidden transfers of energy, where does all that invisible energy flow the next time you watch a puddle freeze or a pot of water boil? The physics of the cooling curve aren't just confined to some laboratory graph, they're happening dynamically all around you, every single day. Keep looking closely at the world, and until next time, keep learning.